Welcome. Let's revise Chemistry Paper 3, KCSE 2024. You are provided with solution A, aqueous sodium hydroxide. So this is sodium hydroxide. Solution B, 0.10 molar of a monobasic acid, B. So monobasic is an acid which contains only one hydrogen in it, and that is an example is HCl. I'm not saying that solution B is HCl, but HCl is an example of a monobasic acid. Solution C, solid C, metal C. Solution D is 2.0 molar hydrochloric acid. Procedure 1. Using a pipette, it is important that you understand the procedure, because if you do not understand the procedure, it is going to be difficult to handle the question. You should be able to know which solution is reacting with which solution. Which solution is reacting? What is the volume of the first reactant and what is the volume of the second? So those are the things you need to understand. Using a pipette and a pipette fill. So when I'm reading, I'm not wasting time. You need to understand the procedure. It is from the procedure we will be able to answer the questions correctly. Using a pipette and a pipette filler, place 25 of solution B in a conical flask. So what we have in the conical flask is 25 centimeters cube of solution B. Solution B is a monobasic acid, which is a monobasic acid B. Fill the puree with aqueous sodium hydroxide. So sodium hydroxide solution A is reacting with solution B. Remember, sodium hydroxide, when reacting with a monobasic acid, the mole ratio is 1:1. That is the reason why they told us a monobasic acid. You should be able to know that. We repeat the titration and complete the table. So we are going to fill the table with the values that I have. So my values that we are going to use, we will use 11.9. Initial, it is important you put it 0.0 always. It is important like that so that to avoid main issues. So my second titer was 12.0 and my last one was 11.9. So when you subtract here, we will have 11.9, 12.0 and 11.9. So this is my values. Remember the decimal point. If I have decided to use one decimal point, let it be consistent. If you vary the decimals, you will lose the marks. Then make sure you subtract this one. This arithmetic is done correctly. So let's calculate the average. Calculate the average volume of solution A. You should remember solution A is the one that is in the burette. Therefore, we need to know the volume. The average we have titrated, and the volume in each titration is this one. Therefore, we need to get the average. Since my volume is very close, I will do the average of the three. So it is 11.9 plus 12.0 plus 11.9 divided by 3. And the answer is going to just press your calculator and write the answer direct to 2 decimal places. Write your answer to 2 decimal places. Calculate the number of moles of the monobasic acid solution B. Calculate the number of moles of monobasic acid solution B. So what information that will help us to calculate the number of moles of the monobasic acid? So let's go back to the procedure. You were provided with solution B, which is 0.10 molar. So what does that mean? It means that the 0.1 molar, this is the number of moles in 1,000 centimeters cube, which is equal to 1 liter. That is what it means. So molarity, remember M stands for molarity, and the molarity is the number of moles in a liter. That is the information that is very crucial, very important in handling this question. Calculate the number of moles of methanol. We know that 0.10 capital M, this is the number of moles in 1,000 centimeters cube of solution B. We have used how many solution B? That is why I was telling you, you need to understand the procedure. You can go back and refer. How much volume did you use? We used 25 of solution B. That's what we have used. That's what has reacted with 11.93 together what we have. Therefore, we ask here 11.93 centimeters cube of this solution will contain how many moles? The one we have used. Remember, the word is the one you used. Now we know that 0.1 capital M. Capital M stands for molarity, and the molarity is the number of moles in a liter. Therefore, 0.1 moles, these are the number of moles in 1,000 centimeters cube of solution B. But how much did we use? We used 25 of solution B. So we will ask 25 centimeters cube of solution B will contain how many moles? So we simply multiply 25 times 0.1 divided by 1,000, and that one will give us 0.0025 moles. So that is the number of moles that has been used from solution B, that we used 25. You can as well use the formula. There is a formula that we have. Moles, molarity, volume in liters. This volume must be in liters. So when you want to calculate moles, is equal to molarity times volume in liters. So the number of moles we want the number of moles of solution B. The molarity of solution B is 0.1, so it is 0.1 times the volume of solution B used. The volume of solution B used is 25, so times 25. 25 is in centimeters cube, but we want in liter. You change it to liters, that is divided by 1,000, and the answer is going to be 0.0025 moles. So you can as well use this formula, and it will give you the correct answer. Calculate the concentration in moles per liter of aqueous sodium hydroxide solution A. Remember, solution A has reacted with solution B. So the mole ratio, that is very important. Mole ratio. So A to B. What was the ratio? 1 to 1. How did I know? Because solution A is sodium hydroxide. This is solution A. Solution B is a monobasic like HCl. So when sodium hydroxide react with HCl, I know the ratio is going to be 1 to 1. That is why that I was using HCl as the monobasic B, so that you know when you write the reaction, the mole ratio is 1 to 1. Now what that means is that the number of moles of solution B would be equal to the number of moles of solution A. So the number of moles of solution A that we have used will be equal to the number of moles of solution B. So it means that moles of A will be equal to 0.0025. Why? The ratio is 1 to 1. Therefore, if what was the volume of solution A used? Solution A, we used 11.93 centimeters cube of A, which contains 0.0025 moles. We will want to know, because molarity is the number of moles per liter. That is why we are looking for molarity, number of moles in 1,000. So we will ask 1,000 centimeters cube will contain how many moles? So it is 1,000 times 0.0025. You divide by 11.93, and the answer is equal to 0.2095557. This answer must be written to 3 decimal places, so you can truncate. So the correct answer, don't write morality, the answer should be in 3 decimal places. So this is going to be 0.209. You can truncate or round off, but I have decided to truncate. Capital M standing for morality. Procedure 2. Using 100 ml measuring cylinder, place 50 centimeters cube of solution of hydrochloric acid, solution D, in 100 ml plastic beaker. Measure the temperature of the solution at a half-minute intervals and record on the table. We have the table here. Then continue measuring and recording the temperature of the mixture and complete the table. Retain. Before I have skipped this Roman 3. At exactly 1.5 minute interval, add all solid C and stir with a thermometer. Continue measuring the recording the temperature of the mixture and complete the table. Retain the mixture for use in procedure 3. This is very important. You need to know if you accidentally pour down or you dispose the solution provided and you have been asking you are supposed to use it in procedure 3, then it means you are going to get wrong information. Therefore, follow instructions. Practical is about following instructions. Now let's look at the table. So what are we supposed to do? Remember, we were given solution D, which is HCl, and we have solid. So this metal is going to react with this, and some heat is going to be released. So the reaction it was actually exothermic, releasing some heat. So let me fill the table for you. So because this is temperature from 0 to 1, the temperature is going to be constant because there's nothing you have done. It will be the solution and the room temperature at that time. So this one will be 23.0, 23.0, 23.0. Remember, temperature is recorded at 1 decimal place. Here, this is X, nothing is there. Now, at this point, we add solid C to the solution and the temperature will start rising. So, in my case, it rose to 35.0, then 37.0, then 40.0, 40.0, and then a drop to 37.0. So by doing that, you get all your 3 marks because there is a trend and the accuracy. So that's maybe you lose 1 mark for accuracy, but this one is very okay. You have maintained the decimal point and there is a trend of increasing temperature, then constant, then a drop. That is what is expected of you. Now on the grid provided, plot a graph of temperature against time. Temperature against time. Now let's draw our graph. I have drawn the temperature against time and I have put a half, 1, 2 to the end. And then temperature, I have broken my temperature. I've started from number 20, temperature 20 to 45. So when temperature now, when time is 0, when time is 0 from here, when time is 0, you can see, when time is 0, the temperature is 23. So here, when time is 0, temperature is 23. So this is 20, 21, 22, 23. So it is here. Again, at a half, it will repeat the same. At 1, it will repeat the same 23 up to here now. At this point, we will put our solid and the temperature will start to rise. At 2, it will rise to 35. So 2, when time is 2, temperature will repeat 35. So you come to 35. 35 is here. You put your mark there. When the time will be 2.5, that is 37. 2.5, 37 is 35, 36, 37 there. When time is 3, that is 40. When time is 3, it will be at 40. When time is 3.5, 3 is same 40. And then when the time is 4, it is 3.7. 37, sorry. That at 4, 37. That's reduced to 37 here. Now, this one can be confusing. So you need to understand when the table has a break, how does the graph look like? Those are the things a student has to know. For this one, you draw a line here. Then extrapolate the line to the point time when you added the solid. So here. So at this point, this is our reference point. So this our reference point here. When the time you added the solid. So this one is our reference point. This is the time you added the solid. So we need to draw a line towards our reference point to get the maximum temperature. So this one, you need to check to draw this one or this. So I will take this one. I will draw the line this and that. Because from the knowledge I have been taught, I know that this line should be like this. So you draw a complete line and then a dotted line like this. Where this dotted line meets the reference point, that is our maximum temperature. That is our maximum temperature. So this is how the graph was supposed to look like. You ignore this one because we know for neutralization it could have been like this. So that's why I told you when the curve is has a broken X, you should know how it looks like. That's very important. Now you read at this temperature and then you subtract. So temperature change will be the initial and final, you subtract. So let us read. This one is going to be 45, 40, 40, 41, 42, 43, 44, and 0.5. Using the graph, determine the temperature change, delta H. So our final is 47 degrees Celsius. We subtract our initial, which was 23 degrees Celsius, and the answer will be 24 degrees Celsius. So our temperature change, our T, is 24 degrees Celsius. That will be our date. So I have used, when you draw like this, you show that you have used your graph to find the temperature change. Calculate the heat change for the reaction. Assume for the solution specific capacity is this and the density is that. So we know that the heat change is equal to mass of the solution times C, specific heat capacity, and then times delta H. That is how we calculate the heat change. The mass, this is the mass of the solution. The solution, remember, we used 50 centimeters cube. So 50 centimeters cube is the same as 50 grams, given that the density is 1, right? Therefore, we divide it by 1,000 to make this 1 kilograms, because I want my heat change to be in kilojoules. 10 times 4.2 times heat change, which is 24. That is the temperature. Sorry, this is times T. That's wrong. Times T, which is times delta T. Then, so this one will be equal to 5.04 kilojoules. So that is the heat change according from my change in temperature. So somebody else could be having some different here, could be having even 20 degrees Celsius. If the student uses the temperature correctly, still the answer for that student is correct. Because in practical, every student's answer is correct. Procedure 3. Transfer all the solution obtained in procedure 2. Now remember the solution we have left here, we had 50 centimeters cube of solution D. This has reacted with C. We have seen the way we have done it. Now the solution, we are transferring it into the volumetric flask. So we are transferring HCl that remained after reacting with C, right? That is very important for you to note. So the solution we are transferring into the volumetric flask 250 centimeters cube is solution D, which reacted with solid C, right? So add distilled water to the mark and label that solution E. So solution E is diluted HCl. Remember that. HCl solution D. HCl solution D is the one which has been diluted. Because you remember solution D was 2 molar hydrochloric acid, which has already reacted with C. So that is. Fill a clean puree with solution C. Remember solution C is HCl, though diluted. Using a pipette and a pipette filler, place 25 of sodium hydroxide, solution A, into a volumetric conical flask. So we are going to titrate solution E against solution A, which is sodium hydroxide. But we know solution E is HCl diluted, right? Titrate the sodium hydroxide with solution E using 2 drops of phenolphthalein indicator. Now, let me fill the table very fast. Our table is ready, fully correctly filled up. So calculate the average volume. Average volume, we'll use 15.8 plus 15.7 plus 15.8 divided by 3. And the answer is 15.77. Make sure your answer is 2 decimal places for the average. Centimeters cube. Centimeters cube. Next question is calculate the number of moles of sodium hydroxide in 25 solution in 25. This is solution A, right? The number of moles. So this one is very important because remember we calculated the molarity of solution A in our procedure 2. So you need to remember that we had calculated the concentration of solution A and the molarity is 0.201 molar. So this is the number of moles in a liter. So we have that, and you must carry this one to the next question, now procedure. So this was procedure 1, not procedure 2. So from procedure 1, we have the concentration of solution A. So let's go to question we were handling. Question. Now, calculated the number of moles of sodium hydroxide solution in 25 used. Because we use solution A, so we know it is solution A. But I have taken you back and I have told you that we had already calculated the molarity of solution A. So 0.209 capital M is the number of moles of A that are present in 1000 centimeters cube. So we will simply ask 25, the one we used here, centimeters cube, will contain how many moles? So this is 25 times 0.209, we divide by 1000, and that one will give us the number of moles, so which is 0.005225 moles. So this is the number of moles of solution A that has reacted with solution E, 15.77 centimeters cube. Calculate the number of moles of hydrochloric acid in 250. That's very important. Now, we know the number of moles which is of A. But this number of moles, first we need to know the number of moles of solution A that reacted with the number of moles of solution E. We know the number of moles of A that reacted with solution E. Now we need to know the number of moles of solution E. Since the mole ratio is 1 to 1, why? Because E is HCl and A is sodium hydroxide. That reaction, the ratio is 1 to 1. Therefore, that means the number of moles of solution A will be equal to the number of moles of solution E that was used. So this was 15.77 centimeters cube. Solution E contains 0.005225 moles because the ratio is 1 to 1. That's very important for you to note. Now, we want to know what is the number of moles of E into 50. So we will simply ask 250 centimeters cube of solution E will contain how many moles? We will simply multiply, cross multiply, that is 250 times 0.005225. We divide this by 15.77 and the number of moles will be 0.08283 moles. So this is the number of moles in 250 solution E, which is very, very important. Why are this number of moles in 250 very important? This number of moles in 250 in solution E will be exactly the number of moles of the solution D that remained after reacting with the solution C. Did you hear that? I don't know whether you know what happened in procedure or 2. Let me try to explain something small here. Remember, 50 centimeters solution D reacted with C, right? We don't know the number of moles of HCl that reacted with D. But now after the reaction is over, we have diluted this solution D to make 250 centimeters cube. Now we have the number of moles of E, which was D diluted to E, right? It means that the number of moles in 250 centimeters cube solution E will be equal to the number of moles in 50 centimeters cube solution D that remained after reacting. That is very important. Therefore, the number of moles in solution D that remained after reacting with C are exactly this one. This is the number of moles in D that remained after reacting with the solid C. This is the number of moles that remained of HCl, the original. Calculate the initial number. This is initial. The initial number of moles of hydrochloric acid in 50 centimeters cube of solution D. That one you go back. We were told that the molality of solution D is this. This is the number of moles in a liter because molality is the number of moles in a liter. Therefore, we will say 2 moles, this one, are in 1,000 centimeters cube. So we will find out 50 centimeters cube. Original, the one that was used was how many? How many were they? So you simply multiply 50 times 2 divided by 1,000. You will find that it is 0.1 moles. So that is the number of moles of the original 50 centimeters cube solution D. Calculate the number of moles. Calculate the number of moles of hydrochloric acid that reacted with metal C. That is very important now. I hope now you are connecting what I was saying. That now the number of moles that reacted with C, this is the original. The original number of solution D was 0.1. 0.1 minus the moles that remained after reacting with solution C, also with metal C. The number of moles that remained is here. This is the number of moles of HCl that remained after reacting with metal C. So we will subtract this, and then we will find the number of moles that reacted with C. So first, let me put this point that moles in 250 centimeters cubed solution E is exactly equal to the number of moles of solution D that remained after reacting with C. This is the number of moles. So we have that is 0.1 minus 0.08 to 83, and the answer is 0.01717. This is the number of moles that now reacted with C. This is the number of moles of HCl that reacted with this. Given that the reaction ratio between the HCl and the metal C is this, calculate the number of moles of metal C. So HCl to metal C, the ratio is 2 to 1. And we know the number of moles of HCl is 0.01717. So what will be this? So this one will be 0.1717 times 1 divided by 2. So the number of moles will be 0.008585. This is the number of moles of metal C that reacted with HCl, because if the ratio is 2 to 1, then it is a half. The number of the moles of the metal is a half that of HCl because of the mole ratio. So the mole ratio. Now calculate the heat. Calculate the heat, calculate the heat of reaction between hydrochloric acid and 1 mole of metal. He simply is asking to calculate the molar heat of reaction, the molar heat of reaction. That's what they're asking us to add. Now, this is very important. You need to know now if this is the number of moles that reacted of C. Remember how much heat was this number of moles was able to produce. You go back to the heat change. So 0.008585 moles of C was able to produce 5.04 kilojoules. So we would want 1 mole, because molar means 1 mole of C would produce so this one is 1 times 5.04, you divide by 0.0085. And this one will give us 585.07 kilojoules per mole. Kilojoules per mole. But since the reaction was exothermic, do not forget to put the negative sign here. So negative shows that the reaction was exothermic. There was a release of heat. Therefore, that is how you were supposed to handle that question, the iteration question. You are provided with solid F. Carry out the following test and record the observations and the inferences in the spaces provided. Place 1/4 of solid F in a dry test tube. Heat the solid strongly and test any gas produced with blue litmus paper. So whenever you are heating a solid, one thing that is produced is a colorless solution. So first you will say, so the first thing is formed is a colorless solution, because when the solid is being heated, moisture is produced which condenses and then form a colorless solution. So you simply write a colorless liquid, not solution. A colorless liquid is formed at the cooler parts of the test tube. So that is important, and that shows that the solid that was heated, solid F, is hydrated. So you can say hydrated substance or solid, or you can say that contains water of crystallization. Contains water of crystallization. Water of crystallization. What will happen to the blue litmus paper? So most probably the blue litmus paper will change to red, or it will remain blue. So in this case, the blue litmus paper changes to red. So if it changes to red, it means that the gas that was produced is acidic. So acidic gas present. Acidic gas present. Place the remaining amount of solid F in a boiling tube, add about 15 centimeters cube of distilled water, and shake to dissolve the solid. Use about 2 centimeters cube or portions of solution in a test tube for each of the following tests. For number 1, to the first portion, add aqueous sodium hydroxide dropwise until in excess. So a white precipitate was formed. A white PPT is acceptable, PPT, which was soluble in excess. So a white precipitate soluble in excess, that means a white precipitate is formed which dissolves when you put in excess. Then when this happens, then you should know what is present is the ZAP. ZAP stands for zinc, aluminum, and lead. So this is zinc 2 positive, aluminum 3 positive, and lead 2 positive present. To the second portion, add aqueous ammonia dropwise until in excess. So the observation was that a white precipitate was formed. A white PPT is formed when the drops were added, but in excess, the white precipitate did not dissolve. So a white PPT insoluble. Insoluble means in which it did not dissolve in excess. Insoluble in excess. So whenever it is if it dissolves in excess, then zinc is present. But since it did not dissolve in excess, then zinc is absent. So if zinc is absent, what could be present? Aluminum and lead are present. These are the ones that are present because when it is insoluble, it means zinc is absent. So don't write zinc absent because we do not want negative answers. We don't want what is not available. We want what is present. Whatever is absent, we don't want to know it. The third portion, add 1 centimeter cube of aqueous sodium chloride, and there was no white PPT. You simply write no white PPT. No white PPT. PPT is allowed even in KCSE, so don't worry. PPTs are precipitate. Instead of writing precipitate, PPT is allowed. So if a white PPT is not formed, then what does it? If there was a white PPT, then lead could have combined with chlorine to form lead chloride, which is insoluble, and it could form a white precipitate. Now that there is no white precipitate, it means lead 2 ions is absent. And if the lead ions are absent because there is no white PPT, then it means that aluminium is the one that is present, because aluminium chloride is a colorless solution. So it means aluminium 3 positive is present. Don't write lead absent, because we don't want whatever is absent. What we want is what is present when identifying metals. Very good. To the fourth portion, add 3 drops of aqueous barium nitrate, shake the mixture, and then add 5 drops of dilute nitric 5 acid. So here, a white precipitate is formed, white PPT, which is insoluble, in nitric 5 acid. So a white precipitate insoluble. It means the white precipitate did not dissolve when the acid was added. Therefore, if it did not dissolve, the white precipitate persisted, then it means that what is present is the sulfate ions. The sulfate ions are present because they are the only one. When you add dilute nitric acid, it will not dissolve the sulfate. But if it was the sulfite or the carbonate, the white precipitate will dissolve to form a colorless solution. You are provided with an organic compound solid G. Carry out the following tests and record the observation and inferences in the spaces provided. Place all solid G in a pouring tube, add 10 centimeters cube of distilled water, and shake to dissolve. Use about 2 centimeters cube portions in the test tube for each of the following tests. To the first portion, add all of the solid sodium hydrogen carbonate provided. So whenever sodium hydrogen carbonate is added, we expect viscing, we expect effervescence. So for this case, there was no effervescence. There was no effervescence. Or you could read, or no viscing, no bubbles. So if there was no, then it means that the acid, then it means that the alkanoic acid is absent. Because if the alkanoic acid was absent, then effervescence could have occurred. So it means R-OH. This is the functional group for alkanoic acid is absent. We write only this. We encourage students to write only this organic acid because we are dealing with organic analysis. To the second portion, add 1 centimeter cube of aqueous potassium dichromate 7,6. Shake well, and then add 2 centimeters cube of dilute sulfuric acid. Heat the mixture strongly, and then allow it to stand for 2 minutes. Here, the orange acidified potassium dichromate changes to green. So the orange acidified potassium dichromate changes to green, meaning that there is what we call ROH, alcohol was present. So whatever happened here is that an alcohol was formed, and that's why the orange color changed to green, indicating that the alcohol was present. To the third portion, add 2 to 3 drops of bromine water. Bromine water only is used to test for the double bond and the triple bond. saturated and unsaturated, the unsaturated only. So if the color changes to colorless, for example, this one bromine water was decolorized. To decolorize meaning the color changes from the original color to colorless. So this means that the double bond or the triple bond was present. Or here, another one student could have written bromine water changes to colorless. So that one is also okay, and the answers is going to be the same. And that is the end of the KCSE Paper 3 2024.